there have been several variations on the original 802.11 Wi-Fi standard. Some have special uses and aren't intended for home use. The original 802.11 is now known as 802.11a. 802.11b came out subsequently and was intended for home use. Other home use variants are G and N and AC. And then we'll talk about each of these in a little bit more detail. Let's see. I think this is just defining some of the talking about some of the definitions of the different layers that we talked about in the OSI stack. The physical, most of these actually use the same MAC layer and the same MAC formatted packet. They differ in the physical layer, the actual frequencies that are used, and how some use orthogonal frequency division multiplexing, others use spread spectrum techniques. Some of the newer variants of 802.11 are capable of simultaneous reception and transmission along multiple frequencies to get extremely high throughput. They can actually combine adjacent channels to get wider bandwidth for greater throughput as well. So some of these newer techniques used in 802.11, we talked about CSMA last time, but DSSS was direct sequence spread spectrum. So if you recall, that's where the digital stream is multiplied by very small pulses in time to get very wide bandwidth and with really narrow pulses. And then another technique, which is kind of like code division multiplexing, using complementary code keying so that we can actually transmit these orthogonal codes, and so we can simultaneously transmit 64 different channels simultaneously without interference. This slide just shows the increase in data rates from the original 802.11, and then I think these actually in the ellipses show the corresponding data rates in megabits per second, going from 2 megabits per second up to this is almost 7 gigabits per second with the latest AC standards. Okay. Not much information here. I think it's just comparing communication data rates and microprocessor speeds, and how microprocessor speeds are still well ahead of the achievable communication rates, but there have been tremendous increases in both of these over the last 30 years, certainly. So this slide is comparing some of the different home networks that are available, home Wi-Fi standards that are used, and in terms of the data rates that are achievable, and then the corresponding bandwidths used by different channels, and then as well as, if you'll notice, the energy consumption has gone down considerably with at least with the latest standards compared to the original standard. And then the other thing that's we've tried to increase over the years is actually there's been a corresponding increase in range from an access point to user, although you'll see that the AC standard actually has a decreased range compared to 802.11n. Again, another slide just comparing the operating frequencies, different modulation techniques, and data rates. You'll see with the 802.11 AC of 500 megabit per second data rate, almost undreamed of, even 20 years ago, to be able to achieve that, a data rate like that wirelessly. So a little bit more on each of these in some detail. So 802.11b was first proposed in 1999. It uses direct sequence spread spectrum and is capable of data rates up to 11 megabits per second in a 2.4 gigahertz band. It did introduce some new security access methods to keep unwanted people off of your Wi-Fi network. Okay. 14 channels available in the specification. Only 11 can be used in the United States due to FCC regulations. So this is kind of comparing the technologies used by the original 802.11 and then the 802.11b. Big thing here was the increase in range, and then there was a switch to a different frequency band from the 5 gigahertz band to the 2.4 gigahertz band. That primarily accounted for the increased range. The higher frequencies are attenuated with distance more greatly than are the lower frequencies. And then the next generation for home use was the 802.11g. Increased data rate of 54 megabits per second, and then it used two different modulation schemes in the frequency bands above 20 megahertz. It used orthogonal frequency division multiplexing, and then below 20 megahertz it used the direct sequence spread spectrum again. And then WPA2 security protocol was introduced with 802.11g as well. Let's see. I think this is actually showing the allocation to 802.11g from the original 11 channels in the U.S. These were divided into 3 channels by 802.11g that corresponded with channels 1, 6, and 11. So it used wider bandwidth than the 802.11b standard. It could, and the N network actually was what's called a MIMO technique, multiple input, multiple output. These would actually, these are your Wi-Fi access points that have multiple antennas. Some of the newer Wi-Fi routers may have as many as 8 different antennas. The antennas can transmit at different frequencies, allowing multiple simultaneous transmissions to different clients. Let's see. These showing some of the different. I think we talked about these different destinations in the MAC header previously, and talked about there being 4 different addresses depending on the mode. In the typical mode, the 2AP, I think this was called 2DS in the previous slide, and from DS are typically both 0, and then the standard addresses are the destination, the source, and then this is the network ID. So the 802.11n used multiple transmit antennas, and so it's capable to focus transmissions and the direction of the client, increasing the signal to noise ratio and also increasing the range of the device. Okay. This is, I think, an advertisement for a typical 802.11g wireless router. 802.11n, again with the multiple antennas for extended range. Okay. And then the 802.11 AC wireless access point has since been ratified, allows the access point to transmit separate streams to each client simultaneously along using separate antennas, so you can get very, very high data rates with the 802.11 AC, approaching the 1 gigabit per second data rate. Okay. This is actually showing an access point. Simultaneously communicating with multiple devices, perhaps even using multiple antennas. You can get some of the 802.11 AC cards for your desktop computer that may have as many as 4 antennas in the desktop networking card, allowing very high throughput for that particular desktop computer. One of the other features of 802.11 C or AC is that it could actually combine adjacent channels to get very high bandwidth. So I think the basic channel width is 20 megahertz, but these could be combined to get 40 megahertz channels or even 80 megahertz channels for mobile systems that actually had high data rate requirements. So I think this is showing up combining 8 of the 20 megahertz channels to get actually a single 160 megahertz channel with the 802.11 AC for a really high speed transmission along that channel. And then this is showing how that can be actually done dynamically with time. Those channels can be split up and allocated for using 80 megahertz channels or 40 megahertz or 20 or 40 megahertz channels on different frequency bands. And I think this is showing even combining even to get 160 megahertz bandwidth channel by combining 8 of these 20 megahertz bands. And I think that's the last slide for this introduction to Wi-Fi networking.